Today we're going to learn how to do the derivative using the fast rules. So instead of using the definition of the derivative, which could take a long time, we're going to be able to calculate these derivatives really fast using these rules. Now I want to point out that we're going to save the product rule and the quotient rule for another day. And for the absolute value rule, we actually have an easier way of doing that. So we're not going to be using this rule really. We have a better way of doing it. You might remember this one from last time, where we used the definition of the derivative for the function 5x squared. We plugged it in, and we did all these calculations, and at the very end, we got 10x. Now today we're going to use the quick rule, so instead of doing all those calculations, we're going to be able to find the answer really quick. The power rule says the 2 comes down, and the new power is 1, so that gives us 2 times 5. The new power is 1, so that would give us a 10x. And that calculation can be done in about 3 seconds. Okay, the first two rules we're going to look at are the constant rule and the power rule. Okay, our first example is a constant function. I want to show you why the derivative of a constant is going to always equal 0. Remember, a derivative is a slope, and if you look at the slope, at any point along this function, the slope of the tangent line will equal 0. And that's why the derivative of a constant is going to equal 0. Now, how do we do the derivative of a number times x? Well, the derivative of a number times x is just going to be that number. And we know that because we know the derivative is the same thing as a slope. We know the slope of a line. A line is written as y equals mx plus b. So the slope of the line is just the number in front of the x. Remember, the derivative is the same thing as the slope. So the slope is just the number in front of the x. So the derivative of 3x is just going to be 3. So the derivative of a constant is just going to equal 0. Here's an example. The derivative of 5 is 0. Now for the power rule, it's probably the most common one we use. When you're doing the derivative of x to a power, the power is going to come down. So you're going to see the 7 comes down, and the new power is 1 less. So the new power is 6. So the derivative of a number times x is just going to be that number. Okay, we're also doing the derivative of 3. Remember, 3 is just a constant, so the derivative of a constant is 0. So it's kind of like a plus 0, but you don't have to write it. Don't forget to multiply the 3 times the 7, you get 21, and we're done. Okay, here's another example of the same thing. We have x to the 8, so the 8 is going to come down, and your new power is 7. When the 8 comes down, you have 8 times 10, that gives you 80. On the second one, the 3 comes down, gives you 27. The new power is 1 less, so the new power is 2. The derivative of a number times x is just going to be the number, and the derivative of a constant is 0. So there's your answer. Okay, now we're going to look at the derivative of an absolute value. Now there is an actual rule for the derivative of an absolute value, but it gets a little bit more complicated when you have something other than just an x inside. Take a look at this example down here. We have a parabola, and on the next graph we have the absolute value of that same parabola. Now I want you to notice that these points down here end up reflecting up here, and after reflecting those points, your graph is now above the x-axis. Now here's what we know about this new graph. The part in orange did not change. It's still the same function. This part in green is the same function, but it's been reflected on the x-axis, so it just has an extra negative in the front of it. So we can rewrite this function as a piecewise function, and each of those derivatives individually are very easy. So if this function represents our absolute value function, then the derivative is just going to be this right here. Notice how easy it is. The derivative of this is just going to be 2x minus 1. Same thing on the bottom. The derivative gives you 2x minus 1. The one in the middle gives you a 2x minus 1, but with an extra negative in the front of it. So that would be kind of like 1 minus 2x. And that's the easier way that we're going to do the derivative of an absolute value function. Okay, next we're going to take a look at the exponential function as well as the log function. Okay, here the derivative of a number to the x is going to be that same number to the x and then natural log of that number. Here's an example. The derivative of 2 to the x is 2 to the x and then ln of 2. Now we're calling this one a special example because when you do the derivative of e to the x, you get e to the x and then ln of e. And what makes this special is that ln of e is 1, so it kind of cancels. So that means the derivative of e to the x is just e to the x. Okay, for the log function, we have log base a of x I want you to notice that we're just using the change of base formula, and then we take out the ln of a. So now we're left with the derivative of ln of x, which is just 1 over x. This ln of a is just like a constant, so it's just going to stay on the bottom. Let's look at an example. The derivative of log base 3 of x is going to be 1 over x, but then you get this ln of 3 in the bottom because it was log base 3. If you use the same rule for ln of x, that's log base e of x, so you're going to end up with an extra log base e in the bottom. But that's just a 1, so it cancels. So that means the derivative for ln of x is just 1 over x. Okay, now we're going to look at the derivative of the 6 trig functions. Okay, for the most part, we're just kind of memorizing these. The derivative of sine is cosine. Derivative for cosine is negative sine. Derivative for tangent is secant squared. The derivative for cosecant is negative cosecant cotangent. The derivative for secant is secant x tangent x. And the derivative for cotangent is negative cosecant squared. Now I do want to point out that the derivative for all these co-functions are equal to a negative. Derivative for all the co-functions are equal to a negative. And the other 3 functions are all equal to a positive. Okay, now we're going to look at the derivative for all the inverse trig functions. Okay, we only have to remember 3 of these. The derivative for sine inverse, secant inverse, and tangent inverse. And that's because you get the same thing for the other 3 co-functions, except they just have a negative. So the derivative for sine inverse gives you the same answer as the derivative for cosine inverse. You just get an extra negative. Same thing for the derivative of secant inverse. The derivative for cosecant inverse has the same answer but just with a negative. And the derivative for tangent inverse has the same answer as the derivative for cotangent inverse, except again it just has an extra negative. So usually we just try to remember these 3, and then adding the word co in front of it will give you an extra negative in the final answer. Okay, now we're down to our last rule, which is the chain rule. Remember, we're going to do the product rule and the quotient rule another day. The chain rule is probably one of the most important rules. Okay, first we're going to look at the chain rule, but we're going to kind of do it the slow way. If you look at the derivative, it's written as dy dx. You can see we can separate the dy dx. We can multiply by du over du. So the first one in the red box is the derivative of y with respect to u, and then the second one is the derivative of u with respect to x. And we'll show you what that means in just a second. Okay, the example we're going to do is the derivative of a function to the power of 10. Now we're going to take all that stuff inside, we're just going to call it a u, so that now our function just kind of looks like u to the 10. Okay, first we're going to do this piece here. We're going to do the derivative of the function, where u is the variable, and that's this right here. We have the derivative of u to the 10, which is 10u to the 9. You'll see I have a special note. Don't leave the u sitting there. The u was all this stuff, so we're going to plug in all that stuff right here. And then the second thing is the derivative of u, so here's u, with respect to x. So we're doing the derivative of that function u, where x is the variable, and that's just the power rule. The 7 comes down, the new power is 6. The derivative of minus 3x is just going to be minus 3. The derivative of a constant is 0. Now that was kind of a long way of doing it. There is kind of a quicker way of doing it. The quicker way is just to pretend all this stuff is just like an x. How would you do the derivative if that was just x to the 10? Well, the 10 would come down and the new power would be 9. Now there's only one other thing you got to do, and that's the derivative of all that stuff. That's actually called the chain rule. The derivative of all that stuff is going to be 7x to the 6 minus 3. So you can do it a whole lot faster if you do it that way. Again, you just pretend this is an x, you do the derivative, and remember, because it wasn't an x, you still have to do the derivative of all that stuff in the middle. When you do that derivative, you get 7x to the 6 minus 3. Okay, now we're just going to do a bunch of examples using all the rules that we learned. This first example highlights the fact that the square root is really just a power of 1/2. Now we're going to have to do the chain rule. Since we have a bunch of stuff inside, we're just going to pretend it's an x. So when we do the derivative, the 1/2 will come down, and the new power will be 1 less. So 1/2 minus 1 is negative 1/2. Now because the inside was a bunch of stuff, we're going to have to do the derivative of all that stuff. That's called the chain rule. Now the derivative of that stuff is 7x to the 6 minus 3. We can rewrite this stuff over here. We can combine it all into one fraction. Remember, the power of 1/2 is the same as the square root. And that's our final answer. Now we haven't learned the quotient rule yet, so we can't do the derivative of a quotient What we can do is rewrite this. If it's a 2 on the bottom and we move it up, it'll become a negative 2 on the top. And now we can do the derivative. If we use the power rule, this negative 2 will come down. The new power will be 1 less, so it'll be negative 3. Don't forget the chain rule. We have to do the derivative of the inside. And that's because it wasn't just an x. It was a bunch of stuff. The derivative of 2x plus 3 is just going to be a 2. Because the power was negative 3, we can rewrite it. On the bottom, it'll be a power of positive 3. Final answer is this. Here's another example. Remember, if you have sine squared of x, that's the same thing as sine of x times sine of x. Again, we can use the power rule. The 2 comes down. The new power is 1 less. If the power is 1, you don't actually have to write it. Don't forget the chain rule. The inside was not just an x. It was a bunch of stuff. So we have to do the derivative of that stuff. If you remember, the derivative of sine is cosine. And that's your final answer. Now, if you're really tricky, you can rewrite this as sine of 2x. But that's a special trig rule that you probably forgot. Most people will just leave the answer like this. Now, in this example, it looks really complicated. But if you remember the rule, if you have ln of x to a power, that power can come down in the front. So this power of sine of x can actually come down in the front. So we have the derivative of sine of x times ln of e. But remember, ln of e is just 1. So really, it's just the derivative of sine. Answer to that is just cosine. So after rewriting it, it became a really easy derivative to do. Okay, remember the derivative for ln of x, just 1 over x. For us, instead of an x, we have a bunch of stuff. So our answer is going to be 1 over that stuff. But then we got to do the chain rule. So we're going to have to do the derivative of that stuff. If you remember, derivative for sine is cosine. Final answer is cosine of x over sine of x, and that's cotangent of x. Okay, we've been going at this for a while, but this is our last example. Remember, square root is the same thing as a power of 1/2. Remember the rule for a log, if you have a power, the power can come down into the front. So this 1/2 can come down in the front. And because it's a constant, you can even bring it to the outside. Now we can do the rule for this derivative. The derivative for ln of x is just 1 over x. We don't have an x, we have a bunch of stuff. So r is going to be 1 over that stuff. We'll bring the 1/2 down. Don't forget, we're going to have to do the chain rule on all that stuff. So we got to do the derivative of 3x to the 7. Okay, now we can simplify. I'm going to break up the x to the 7 on the bottom. I'm also going to break up the 21. The reason I'm going to do that is so the 3's cancel and the x to the 6 cancel. You might be wondering, how does x over x cancel? Well, it's because x cannot equal 0. Here's our function right here. Clearly, x cannot be 0. After canceling, we're left with 7 over 2x.